Hello and welcome to Group 1 CSCI4050U Machine Learning Final Project, Beam Me Up. In this project, we will be talking about forecasting alleged UFO sightings by location and date. First, let's dive into the learning problem. This machine learning model predicts the number of UFO sightings in Canadian provinces and American states during 2016. The model covers a supervised regression problem. The neural network learns temporal patterns, such as the months that have more recorded sightings, and geographical patterns, such as the states or provinces that historically reported more UFO activity. The regression task includes the output numeric prediction, including the daily sightings. The goal is to learn temporal and graphical patterns in UFO reportings, estimating a numerical value like daily sighting count. Next, let's get into the dataset exploration. The dataset is retrieved from Kaggle.com, which includes 5,177 entries and includes the date and time, country, city, state, shape, summary, latitude, and longitude columns. In the dataset, date fields appeared inconsistent where cleaning was included. Rows with missing date and time are dropped from field parsing. More cleaning was included where if there were bad rows that are considered bad, we drop them. Key features were extracted from the date column. The dataset is then grouped by state for more detail and samples. One-hot encoding is used to create columns to feed the model, and matrix X and target Y is then created. X is then normalized to take input features and standardize them to retrieve the mean and standard deviation, required for neural networks, help linear regression, and prevent bias towards high magnitude features to ensure the model can learn efficiently and correctly. The train/test split will split the dataset into training and testing to avoid overfitting, provide valuation metrics, and provide reporting results.
Our first step was converting our NumPy arrays into PyTorch tensors. We then used a data loader to manage the data. This data loader's main job is to feed the model data in small batches. It's crucial because it allows the model to learn efficiently and prevents it from overloading memory. Our model is a multi-layer perceptron MLP designed specifically for regression. The network has 62 inputs for our time and state features and one output neuron to predict the count for sightings. Since sightings must be 0 or some positive number, we used a final ReLU activation on the output to prevent negative predictions. We trained the network using the Atom Optimizer and the mean squared error MSE loss. To ensure the model learned generalizable patterns, we implemented the following training loop. We tested performance against a validation set, which is the unseen data to the model at the end of every epoch. This allowed us to immediately check for any overfitting. In the loss plot, as seen on the left, you can see the training loss in blue and the validation loss in orange dropping and staying close together. This shows the model generalized well to unseen data. In the error plot on the right, similarly, the mean absolute value error curves for training and validation. This low MAE is what we used for our prediction confidence in the deployed widget. The relatively low error confirms the MLP effectively learned to forecast sighting counts based on location and time. So with that, we can jump to the demo of our Google Colab interactive widget. For our deployment, we investigated possibilities like a simple web app or a Python script, but ultimately landed on an interactive widget built into Google Colab, seen as we had already built our model on the platform. The widget, UFO Sighting Predictor, demonstrates how our trained network can be integrated into an application for real-time forecasting. When the user selects the state or province and selects the date, The system executes the entire pre-processing pipeline defined during our data cleaning phase. The script extracts all required temporal features from the date, for example, the day and month. It then handles the one-hot encoding for the selected state or province, for example, QC, which is Quebec. This ensures the location data is properly formatted for the network. It uses the original scikit-learn scalar object to normalize this input. This step is crucial as it ensures the input is scaled in the same way as the training data. Once this input vector is prepared and scaled, the model is executed. The normalized vector is passed to the trained model, which performs a forward pass to generate a new prediction. For example, if we select the state of VT, which is Vermont, and we select a date such as April 8th, and we select new predict sightings, it gives us the date, April 8, 2016, state province, Vermont, and then a predicted sighting of 2.56. Because our model is using regression, we use MAE, or mean absolute error, to understand its confidence. The MAE value shown, which it shows to be about 0.56, represents the average expected error margin from our model during testing. This level of MAE is translated into a low confidence warning, as seen here, providing the user with a realistic expectation that the actual number of sightings could be half a sighting higher or lower than the prediction. This transparency is essential for a reliable system. Additionally, the model then rounds its prediction from 2.56 up to approximately 3 sightings.
The supervised regression model is used to forecast UFO daily sightings counts in Canada and the US during 2016. A structured dataset prepared extensive data cleaning and feature engineering. UFO sightings are seen as uneven, where 77% of days have 0 to 1 sightings, which can make predictions challenging. Summer months show higher activity, as well as New York, California, and Florida showing higher activity. Classic models can outperform neural networks when data is limited. Linear regression has the best overall performance. Scaling, encoding, and grouping is important for accurate predictions. Overall, the models had the ability to catch basic temporary and geographic patterns in UFO reports. Linear regression shows best performance to provide simplicity, balance, and predictive accuracy.